Thank you for coming for my talk. So first of all, I always said this is the most important slides because it got the link to the whole slide deck, and also there's like all my social media presence. You can if you have question, for example, tomorrow when you wake up you have a question, you can still DM me on Twitter. Mastodon is the same handle, but I don't check as frequently as Twitter, sadly. But we check both basically. We are going to profile our data science work, and how it's going to work, I'm going to show you. But first of all, so this is me. I'm Cheuk. I work for Anaconda. I used to be a data scientist, but now I am developer advocate at Anaconda. I love open source project. Also, this morning you have heard, that we have to support non-focused projects, so please talk to them in the booth. Also, I help organize a lot of conference because, again, I love the community. So who have been there? Who have seen this era, Memray era? Yes, we have all been there. Every time we saw that, it's it's almost as bad as seeing the blue screen of death, right? It's like, oh my God, I have to run it again. Oh. So, yeah, that's why we have to do memory profiling. And what is memory profiling? So before I really show you how it can be done, you may, for those of you who got really good eyesight, you may also see that I have a tab open. There's a Jupyter notebook, but I'm going to show you after. Before that, I want to talk about what is profiling, for some of you who haven't heard about the term before. In software engineering, we do profiling, which is actually investigating our program's behavior. So usually it's kind of something that we inspect your program when it's being executed. So that's why sometimes it's also called dynamic analysis, because it's actually what is really happening. It's not because of your code. You analyze it because of how you write your code and stuff, but it's what is actually being executed. And so we have tools to do that. We have tools to inspect or monitor your code when it's got executed. It's called Profiler. So there are actually many different types of profiling. You may have heard of C Profiler or this different thing that people use. But today, we're going to focus on memory profiling. So like I said before, profiling, we're monitoring our code. And for memory profiling, especially, we are looking at how the memory is being used when we execute our program. So it's about memory allocation. One thing that's always been talked about is the garbage collection, because when some memories that has been used and is not needed anymore is supposed to be free and get rid of the stuff you stored there before, that's garbage and you have to collect them so you free up the space. But it's not always going to happen perfectly. That's why it's always got talked about, because things may go wrong and we really want to get it done right. So when the program gets executed over time, we want to make sure that all the memory is being used efficiently. There's, you're not going to get that memory error again. So that's why we want to investigate. We want to see what's going on. So why we need a memory profiler? Especially, I think there's something that has been overlooked when doing data science work. We are all data scientists. We all care about the statistic, about getting all this analysis, telling the story from the data. But sometimes we forgot that we are also using the computer, and we should actually think about how the computer is doing. Is it going to surface perfectly, or is it having some hiccup somewhere in your code? So, for example, data science work, you may have done it before. You load a super big, data set. We have to handle a lot of data. Sometimes we run out of memory very easily, especially on older machines. Nowadays, machine or cluster, whatever you use on the cloud, are very powerful. You can always spin up a bigger one, but you may be paying more if you're spinning up a bigger cluster. So you may as well see if your code is, doing the proper thing and optimizing all your memories. So Python apps, we all love Python. Python is very easy to use, but Python, because it's so user-friendly, sometimes we kind of obstruct and didn't look at, at a low level, is our memory being managed properly? We can't really have the transparency to see it. So a lot of times, when we're not careful, we get that memory error. Or even worse, because we are doing scientific work, a lot of the tools, the libraries that we're using actually have a lot of external plugins that's probably not, within, or written in Python or something that is written in some other languages. So sometimes, we may get something that, oh, it takes forever to run, but I don't know why. At the end of the day, you don't have the patience, you have to kill it. It may be because actually you're running out of memory, but because of the communication between the plugin and Python, and then somehow it doesn't get raised, the error doesn't get raised. So you're just waiting there forever for nothing. So it's not good. So we need to know what's going on. So before you kind of deploy your work, scaling it up, we have to do our profiling. So a lot of terms getting involved when we kind of starting to do profiling. You may see them online all the time on Stack Overflow, whatever. When you ask a question, people talk about this all the time. Heap and stack memory, what are they? So I am trying to so this is what I found out. I try to do a comparison. So heap memory, usually it means that it's just like a big kind of bubbles or sea of variables. They're global variables. They can be stored anywhere. There's no structure to it. So that's why you need a reference. Otherwise, it's kind of lost in the abyss, and then you kind of don't know where they are, and then you don't know that they are not needed anymore, and you forgot to collect them, which is the garbage collection. So these need to be free. If a tool or a program that's do it properly, then all these garbage will be collected and free up the memory, so you can do more stuff. Or if you kind of, for example, again, something happened and you have no patience to wait for the program to finish and you killed it, then, well, it will be free because your process got terminated. It's basically done by the operation system. So it's like something that is not about your program. It's about, you killed everything, so they all got free up. On the other hand, there's stack memory. Stack memory usually is for local variables. So that's why local variables, when it's outside of the scope, you can't access those variables because they are stored in stack memory, and they will be free when your function returns. So outside of your function, it's gone. You don't have access to it anymore. But those, there's no problem of forget to collect the garbage because they are in order. So once your function is done, all of them will be erased. There's less problem of this kind of leakage of memory. So another thing that got talked about all the time is the residence set and virtual memory. Wow, it's so fancy, these terms, I love it. So residence, what is it? So residence means that how much is actually used on your computer RAM. So sometimes it's something that, virtual, you may compare all physical and virtual, so it's something that's actually used. Because nowadays, computers are very smart. If you are not doing something yet, for example, you haven't loaded in a CSV yet, you don't have to hold up that kind of space, or sometimes even more low level, your computer will swap all this memory around when it's not being used. It's going to be storing something else before it got to be used. So basically, it's just making more efficient. So sometimes you can run a program that actually requires more memory than actually the RAM you have on your computer, because of this resident and virtual memory thing, because things got swapped around. So residence, about what is actually being used at the moment. Virtual memory is the whole process, how much memory is needed for the whole process to be finished. So that sometimes, like I said, may be bigger than what you actually have because things got swapped around and stuff. So that's why sometimes looking at it, you have to bear in mind that what you are really using, what is really needed. So for example, resident memory, how much it's using, you can actually got a really reliable estimate of whether you're running out or not. But for virtual, you may compare, program which one use more memory at the end of the day, but it may be not reflecting how much memory you're actually using at any certain point of time. So to make it more complicated, different operation system may be different as well. So I'm just giving a general idea here. So for what actually is happening, it really depends on your computer. So it's very difficult to explain everything. So I'm just giving an overlook at this point. So how does Python do all these complicated things? Python can be installed in my machine, in your machine, on different operating systems. So Python actually did a pretty good job of making things work on different operation systems with the memories. So I hope it's not too small. I don't know why it becomes so small. But anyway, so Python actually stores objects with a very, very interesting mechanism. Python, first of all, it will have a private heap. So I will explain more in detail. So there's things called arena, and then all these Python objects are actually blocks. You can imagine as a Lego blocks that they kind of fill up this arena. So in Python, we have so you may heard this name before, PyMalloc, which is actually the Python memory manager that is built in. it is kind of like the higher level kind of things, and then below it, there's actually other like C APIs that's like, so complicated that I don't even understand, so I won't explain that to you. So it's like PyMem, raw, malloc, that kind of thing. So I won't look at the C code because I'm not very good at C. And then after that, it will actually talk to your, your machine's management system, so virtual memory management manager. So those are actually like OS dependent. So different type of Python object, actually, they would have a different size. For example, so this is how PyMalloc work. So actually, PyMalloc is designed for small objects. So the maximum size of the objects that can work with PyMalloc is 512 bytes. So that's a defined amount of size. It can be smaller, can't be bigger. So that's the maximum size of the block for your Python object. So all these blocks, like I said, they are filling up this arena. So everything is kind of managed like block by block. So it's a very organized way of doing it. The advantage is, very easy to implement, very quick, to access and stuff, but may not be the most optimized things to do. And also, if it's bigger than 512 bytes, then it will fall back into using other more complicated things like the PyMem, raw, malloc, or the other things. So also the size is kind of like need to be a multiple, of A. So it's from H to 512. So, because they are blocks and they can only like be stacking, kind of in units. So that's all the technical details. But we want to know how we can actually use it, right? How are we going to do it when we are using our Jupyter notebook, doing some data science work? What are we going to do? So I found a tool that actually can do the memory profiling, and it will work in your Jupyter notebook. So this is Memray. I'm not involved in this project, and so I'm just telling you because it works with Jupyter notebook. And let's see how it works. So I have this code here. I can also put the link for this slides and all this code in Discord later, so don't worry about it. If you want to try it at home, you can download the code or something. So I'm going to show you the first one, which is explaining some kind of basics. So when you're using it, how I'm going to look at it, using it is very easy, but how to interpret it is a little bit, require a little bit of knowledge. So like I said, this tool works with Jupyter Notebook, so there's actually a plugin that you could use. So we have all used this percentage magic before, just like, for example, Matplotlib, you have used the percentage magic, so it's kind of like that. So you load in an extension. Of course, you have to have Memray installed. It's taking quite a while. I don't know why. Maybe I'm running off memory. So, yeah. Why? Please. OK. I'll just run the cell, and hopefully something will happen. Yeah, why is it taking so long? I think maybe I'm... Oh, yeah, it's starting now. Yeah, it's very, very slow. Usually it's not that slow. I think I opened too many tabs. Like you'll see at the bottom, you see. I'm trying to demonstrate what happened when you run out of memory, okay? No, I'm just joking. So this is an example that they show in their official documentation. So it's kind of showing you how it looks like when you use this percentage magic and to get a frame graph. So what is a frame graph? A frame graph for people who, like developers who have done this kind of like profiling work before, of course, they're not, they're familiar with it. That's not new for them. But for data scientists, it may be something very new. And this is, I'm zooming in too much, but don't worry, I have a solution for that. But anyway, look at this beautiful frame graph. We have, everything is blocked. So you can see that actually for each function. So I'm looking at it like kind of top down. You can revert it, like you can flip it over if you want. But what I'm doing it here is to showing you that, for example, if this function is calling something that's kind of like is showing below it. So for the most bottom one, for example, this one is actually the deepest call. If you look at this, right, there's a very, kind of, not iterated, but like layered kind of structure. You can see the last call are C and D. So it's like A times N. It's very silly, but it's a demonstration. So say these are C and D, right? So they are the deepest core because everybody is calling them layer by layer. There's how it will look like in a frame graph. So if you want to look at what is the deepest core, look at the bottom of it, right? Or you can flip it around. I forgot how to. Or you can flip it around like this. This is more like, a tower, if you can imagine. So the other is like a well. This is like a tower. So to look at something more complicated, let's run this example. Okay. So here, you see that this is a little bit irregular because now we are doing things that are more complicated. There are different things, not just A times N all the time, but sometimes they're different sizes. So that's obviously that they will be using different amount of memory. That's why it's like kind of irregular in this example. So we call this this edge that has nothing on, well, let's invert it because the term make more sense if we inverted it. So this we call it a roof because there's nothing on top of it, right? There's the deepest layer if it's got inverted. So we want to look at those roofs. Reason being that roofs kind of show you what is occupying the memory. For example, if you see that, for example, this one, so this is actually the core, if you believe me, right? It's kind of too big, but it's actually F. So F is calling G. So basically F is doing nothing except calling G. So, but G is doing something, right? So you can see here that this is G, this is F. So G is sitting perfectly same size on top of F because how much memory F is using is how much memory G is using, right? So, it's just doing nothing but calling G function. So that's why it's this. So when you look at this way, then there's nothing for you to optimize in F because, well, if you can optimize G, it basically optimize F, right? But for an counterexample is something like this one. So this one, so if you believe me, because the box is too big, is actually D. So D is doing a bunch of things. So you can see D here. It will have other functions as a roof. For example, this one, I believe, yeah, this one is E, and this one is F. So E and F is another box that sit on top of D. So they are not the roof of D because there's something on top, right? But D actually got its own roof here. This small edge is D's roof. So it means that you can actually optimize D. If you can optimize D in some way that get rid of this roof, then it will be more efficient. Then it's just up to E and F. So that's why it's very important to find out this roof and to see where you can improve or optimize your code. For example, you write a bunch of things and then you see that, oh, actually you got a big roof somewhere, then maybe I can improve that a little bit, change things a little bit and see if that could improve things. That's very abstract, isn't it? So let's look at something more practical. So I have another thing that, I love ice cream, by the way. So I always use the ice cream as an example. So I'm going to run a bunch of cell because it takes a while because of my fault. I'm so sorry. Let's look at the code first while it's running. So I'm doing something, I have some CSV, which is about ice cream review and products. I'm going to load them in using pandas. And I'm just going to run this bunch of things. It's just pandas, nothing very interesting. And look at this here. Oh, it's done, okay. So you can see it's just a pandas data frame. We're all familiar with it. So this is something that may be something similar to what you do day to day, cleaning up the data. For example, this one, I want to get yearly stat, right? Because, all this review, they are very detailed, but they are also like at different dates. I want to congregate them into different years so I can see how each ice cream is doing, whether it get more popular this year, less popular this year. I want to have a look at that. So what I'm going to do is the most, straightforward thing is like because this is a string. I haven't shown the D type here, but if you show the D type, this is a string. So I can actually cop out the first 4 letters. They will be actually the year, right? So I'm going to, I can group by using that. So that's what I'm doing here, right? But there's another way to do it, is how about I do it properly, in quotation, convert that string into a date, and then I just get the year of it, right? So this is the second way of doing it. So I have 2 versions of doing the same thing. And I'm going to, so this is doing all the join and stuff, I hope you are familiar with it because you're all doing data science work. So so it's just, doing a bunch of group by and then join together. So this is the first version that is just copying the first 4 letters of the string. So let's see how it performs. So you can see the frame graph here. Oops, I think it's this one is very complicated, right? So because like Panda is doing a lot of complicated things that we are too scared to look at. But you can see that we have this thing, right? This thing we know because it's calling get year stat. This is using the first method, which is getting the first 4 letters of the string. And I want to compare it to the version 2, which is converting it into a date. So how does it different? I'm doing the same thing. I can have a look and comparison. And yeah, so this is here, so this one. So you may see that, oh my God, this is like, how can you look at this? Well, if you really don't want to look at it, one thing good about it is that all the results actually are saved as an HTML file. So for example, this one, if I look at it, it's saved to, so TMPA something something, so can I find it? Yeah, this one is actually the same frame graph. It's in an HTML file, so this is easier to see, I hope. Yep, so this is easier to see. So yeah, this one is the one that I get it, convert into a date, and then it's a year. So you can see, compare these two. So this actually, is costing, how much is, it's still too big. Sorry, let me zoom out a little bit to see if it's better so I can see. No, it's not. Let's revert it. And yeah, the one thing I don't like about this, like, because it's, it's too long. I really can't see much. And then I can't really zoom in and out to have a better look at it. But you can see, I want to compare this one. Okay, what I can do is to run it again, because sometimes the order will be swapped if I run it again. Yeah, now it's like kind of in a hacky category, right? So, okay, now you can see that it's using 3.2 megabyte. So, is it mega? No, it's MIB. I don't think it's megabyte. It's not using that much. But anyway, 3.2, right? Remember this. And then we compare it to the first one, which is this one here. It's using 1.2. So, actually version 1 is better. I've just copied the first 4 letters, and it's like, actually if I convert it into a Python data object, it's actually using more memory. So now you know which one you should do. If you don't care about doing it properly using the date object, if you just want to quickly do a group by, you know what to do. It's very, quick to just, so my instinct was right. So this is what I would normally do, just to copy the first 4 letters and do a group by like very quickly. And this is actually the more efficient, in memory perspective, more efficient way of doing it. So now you know, and you have proven that, after years of data science experience, I'm actually doing it more efficiently. Yeah. So, so this is basically how you do it. Of course, it's a bit difficult at the beginning. It's a bit scary, so many calls and stuff. But I hope you can try doing it. It may help you to solve some mystery. Sometimes, why is using up so much memory? Because sometimes you're doing some kind of pivot table, or like joining different data frames, and then why it's got frozen up. This may be why, and you may investigate, and somehow you may be able to squeeze your CSV into a small enough memory to be working in memory instead of spinning up a bigger cluster and cost more money. So you can tell your company, I save money, all right? So this is quite good. So I think that's all I have to say about memory profiling. The last thing I want to tell you is about EuroPython, which is a conference that I've been organizing in the past few years, and this year is going to be in July, and it's going to be amazing in Prague. And tomorrow, I hope someone's going to tell you more in the lightning talk, I hope. So, or if you have any questions, talk to me. I have Anaconda pen. If you talk to me about Anaconda, I'll give you some swag. So that's it. Thank you so much. Is there any questions on slide?
Thank you so much for a very memorable talk. I'm so sorry I had to.
Back to the top for you.
There are actually 3 questions, 4 now, 5. They're currently coming in, but maybe we can already get started with one. Can Memray show runtimes as well on the x-axis? Do you know that?
Runtime on the x, so the x-axis, you mean this one, right? Yeah, so this actually now is not in order. You can see that if you run it the second time, the order will be flipped, so they are not actually the order that has been executed. It's just like if a function is calling another function, so that's the order of execution is on the y-axis, not on the x-axis. So the x-axis doesn't mean too much. It's just for comparing how much each process is causing you know, if a longer, you know, if the box is longer, it means that it's using more memory. So that's the x-axis. The y-axis is like actually the calling order.
Then the next question would be, how does this work with parallel implementations? Is there a fancy
Yeah,
thing?
I mean, it actually, you can, I think there's like a thing you can flip to look at the parallel as well, if I remember correctly. Let me have a look at one of the things, see. Yeah. Oh, I remember, no, actually there's some settings that you could allow. So if you look at the documentation, right, Memray documentation, they would show you that actually there's some like parameters that you can add to this percentage magic to turn on like parallelization or these other things that you could, you know, because I know there are lots of data science tools that actually is using a lot of optimization to do maybe parallel or like, you know, pre-compile stuff. So those parameters may help you to investigate more. So yeah.
Is Memray the most commonly used memory profiler, and what are other good solutions?
Yeah, I do come across others, but I haven't looked at them in detail. I look Memray in detail because they work with Jupyter Notebook. They just, you know, because when I get interested, I've heard like one of the core developer announced that Memray now have a Jupyter Notebook plugin. So of course there are other tools that can do the same thing, but it may not be as easy to use on your Jupyter Notebook as Memray. There are also other profilers as well, which like not just looking at memory, but also like maybe the speed, other performances, but you know, so. But I kind of like Memray because it worked with Jupyter Notebook. Yeah.
Is there a way to process memory output data non-visually? Somebody wants to export it into a data frame.
Ooh, I think you can export it again. Like look at the documentation. I think you can export the report as well. Now you can see that like all these frame graph is generated as an HTML, but there's other format that you can kind of output all the results. Yeah.
Related to getting things a little bit less cluttered, is there a way to only say profile my code and ignore the underlying functionalities?
There's actually like you can see there's like, oh, hide these like system frame, but it doesn't, it helps a little bit, but it doesn't help much because again, like a lot of them are not considered as system frames, it's just pandas doing panda things. So yeah, it helps a little bit, but not like perfectly. I know what you mean. Like, oh, what if you just show the code that I'm explicitly written here, right? Unfortunately, it's not going to be, but if you check this, that it will hide some of the stuff that's like even more complicated than the pandas internal, so yeah.
I guess we have time for one last short question. Do you know if there's a Spider plugin for Memray?
Spider, oh my God, I have to confess I haven't used Spider for a long time, so I don't know. Yeah, sorry about that.
Okay, thank you so much.
Yeah, thank you.